Alright, I hope you didn't think we were done with the comparisons here, because we got plenty more coming up. The statement reads, compare equations 2.15, 4.9, and 6.11, and notice that if rho, p, and m are uniform, the same integral is involved in all three, i.e. the separation vector hat divided by the separation vector squared, d tau prime. Therefore, if you happen to know the electric field of a uniformly charged object, you can immediately write down the scalar potential of a uniformly polarized object and the vector potential of a uniform magnetized object of the same shape. So use this observation to obtain V inside and outside a uniformly polarized sphere and the vector potential inside and outside a uniformly magnetized sphere. Okay? That's really handy because this same integral keeps popping up as you might have expected. So let's first start by stating what these equations are. The equation 2.15, which of course would vary book to book, is for the uniform charge density. The electric field is E equal rho 1 over 4 pi epsilon naught integral that we just discussed. Equation 4.9 for uniform polarization. The potential is equal to the polarization dotted with 1 over 4 pi epsilon naught times the integral. And then equation 611 for uniform magnetization. This is A is equal to mu naught epsilon naught m cross the 1 over 4 pi epsilon naught integral. Okay, so if we're just going to list them out, what we see here for a uniformly charged sphere with radius r. Inside and outside, they're a little different. As you might imagine, you still have to have that ratio when you're outside. Okay, so then the scalar then is pretty simple there. Again, just keep that big R cubed over R squared ratio with you. Note that you have P dot R versus P dot R hat. Again, you're going outside, so you're just in the radial direction. And then similarly here, we just have, again, that ratio R cubed over R squared for the vector potential outside, but it's still M cross R and M cross R hat when you're outside. Pretty quick, pretty painless. Keep this in mind when moving with these integrals.